A very good day to you all, and a warm welcome to the free webinar on Zero Carbon Concrete, Latest Developments in the World, a collaborative effort between Structural Design Institute and our esteemed partner, Civil and Structural Engineering Consortium. A very good day to you all, and a warm welcome to the free. If this is your first time with us, SDI is an educational institution that has a lot in store for you. We specialize in engineering covering areas such as design, construction, and software training. What sets us apart is our close affiliation with civil and structural engineering consultants, a name synonymous with excellence in the field, having worked on several iconic projects in Sri Lanka. At SDI, we are committed to the continuous professional development of engineers. So we offer CPD courses and events for those pursuing charterships or looking to enhance their skills. You can see a few of our ongoing and upcoming courses here. At SDI, we are focused on structural analysis and design, architectural modeling, and even some courses focused on specialist topics. What sets us apart from other similar organizations is our exceptional faculty, as our educators are all practicing engineers with extensive real-world experience, some of whom are even renowned in academia. We also offer a set of publications, including tall building guidelines for Sri Lanka and construction specifications for tall buildings in Sri Lanka, as shown on the screen, with more to come. The first webinar organized by SDI for the year 2025 will be conducted by an esteemed professional in the industry, our very own chairman, Professor Priyan Mendes. Professor Mendes needs no introduction as a renowned researcher and valued contributor to the industry. He holds the esteemed position of Professor of Civil Engineering at the University of Melbourne and is widely recognized as a leading expert in structural advanced manufacturing of prefabricated modular housing, where he continues to push the boundaries of innovation and sustainability in construction methods. His expertise spans a wide range of disciplines, including prefabricated structures, tall buildings, durability of concrete structures, advanced materials for construction, including waste material, sustainable construction materials, protective technologies for construction, and many more related to high-rise design. Before joining the University of Melbourne, Professor Mendes made significant contributions as a structural engineer at Connell Wagner Ltd in Melbourne, and his career highlights include consultancy roles in the design of iconic tall buildings worldwide, such as the Burj Khalifa, Merdeka 118, and the Eureka Tower. Beyond skyscrapers, Professor Mendes has also lent his expertise to major infrastructure projects in several countries, especially in Melbourne. Professor Mendes is a prolific researcher with over 450 papers published and more than 16,500 citations to his name. His impact on the field is underscored by his supervision of 66 successful PhD students and his recognition in the top 2% of researchers worldwide, according to the database compiled by Stanford University, Elsevier. Please join me in welcoming Professor Priyan Mendes to speak on the topic of zero carbon concrete, latest developments in the world. Over to you, Professor.
Thank you very much, Engineer Andrea, and also Engineer Chatumi for organizing this webinar. It's a first for the year for the Structural Design Institute. And again, also warm welcome to, actually, in fact, a number of senior professionals are here, and also thank you for the other staff as well joining us. There's another group upstairs, fourth floor. I think you're linking with the other computer. So warm welcome to all. Also, there's online audience. The webinar is for the online audience, but really thank you for joining us here. And I was very happy to do it from here, Colombo. This topic is, I think it's okay to say, I also go around in different places. No one has presented this topic in a conference or so yet in the world. So I think it's a world first of this topic. There's low carbon concrete, but not zero carbon concrete. No one has presented. So I took the opportunity here to present it from here, from Colombo, which is really, I'm privileged to do that and to be part of the, in fact, the CSEC family as well here. And with this topic changes, a lot of things are changing the world. I'll stick to about 40 minutes, and again, and then we'll have a bit of a discussion session. And with the topic that is more of is the materials to structures, and that is the trend now to go from materials to structures. We can do all the work which I'm going to cover today. We can do all the work on materials, but then we need to really finally look at the structures as well. So with that's the theme of this talk, and it's really a growing area. We will see a lot in next few years. And again, I think I'm doing another talk in Korea in May, and they have invited me to talk about this similar topic. But I will be the first to be from here. I'm delivering this talk. Just my career-wise, with the you may have heard about this before, but otherwise there are a number of people joining online as well. For the first time, I'm sure. With the telecom corporate building, first when I was a project engineer for this building, it's really probably one of the tallest at that time. I used high strength concrete first time in Australia, 65 MPa, and I got an award from the Concrete Institute for that outstanding service contribution award in 2017 for that work. But this was done in 90s. But then the second one was more, I will just touch on that today. I will not talk about too much on that. The Burj Khalifa, where the columns, the world's tallest building, the high strength concrete columns were based on the work done at Melbourne University by my group, and I show maybe just briefly. And also the Eureka Tower, Australia's, we can still call it the tallest building in Australia. High strength concrete, everything is based on my work. And I was part of the group as well, the design group for that building. So it's we use 100 MPa per walls and all that. And then the Lotus Tower, of course, I was there from day one with Mr. Shomal Fernando from day one in that project. And then again, the modular structures, which I think I will not have time to talk today. It's on another topic, but really you do that in the factory and brought to the site. And that is really Mr. Tilak is there. He's the Sri Lanka leader now, director, research director, technical director of ICC, who is running the first prefabricated modular plant in Sri Lanka, doing very well. I was there a couple of weeks back, and we'll see a lot happening through that modular, the ICC headquarters coming up in Marine Drive and many other buildings on modular. And I was very happy to be knowing Mr. Tilak for a long time and working together. And in some ways. Anyway, that's a brief introduction. Congratulations to Structural Design Institute having a very active program last year. And we see a lot of people have benefited from that. And I'm sure that work will continue this year as well. So coming back to, that's my whole group. If I summarize my group there, wider group, I think, I don't know the exact number, but I think must be close to 50 in my wider group, not just, I directly supervise students, but my wider group. So it's it's really, we talk about the concrete technology. I'll explain today why concrete technology is so important, and then also where we are leading to in the next decade. And so this is the area which is the most difficult one. We can do a lot of things in the lab now. And so by pushing the limits with these materials to structures to lab to field is the most difficult one. That's why I'm focusing on. I do a lot of work in the lab, my group, but lab to the field applications and standards and specifications are a key to really get this to the practice. That's what we all want. We can be academic, but main thing is to really try and get to the field. That's the most difficult task. So materials to structures, and again from material level to the structural level, and then structures back to the materials level. So we need to really look at the structure, reverse engineer to have from structures to the structure to the material level. So this is again, it's a difficult task sometimes looking at the structural performance and back to the materials. So we can do a lot of things here. And one of the things that why the here is easy for me in Sri Lanka, the reason is that other countries it's very hard to go and do like monitor things happening in the buildings. The property managers are not easy to work with. I don't think they're listening today. Because they have the risk for a building. They have they are managing the property, so they've already, if you monitor, there could be some problem in the property. But here I don't have any problem. We can go and do monitoring of the buildings. Capital Twin Peak is a good example where the monitoring is done. We started doing the monitoring, the CSEC project, the design project. It's been still some monitoring being done right through. There are so many examples. Lotus Tower has the anemometers at the top of the building and accelerometers. So ongoing monitoring anyway. This is all part of the whole thing. And concrete can do many things. On the left-hand side it's in Portugal, and you can see amazing concrete structure there in the pavilion for the expo. And so that's where we can, today I'm not going to talk about too much on that. But then the next one will be on the other side is where the world is heading, automation in construction. And we need to, once you develop the materials, we need to be thinking about the 3D printing on site. 3D printing you can do in the lab, but to be doing the 3D printing in the on-site is the most difficult task. So that's where we can, and we need to, when you develop materials, mixes and all that, we should be prepared for the future. We don't need to worry too much yet, but it's going to come to the world. I'm talking about the next decade as well, not just what's happening today. So these are all coming up in a big way. Just a very quick comment on the left-hand structures. We call it textile reinforced concrete. That is where we have the cementitious product, and then we have the reinforcement is like the composite fibers. So the cementitious material protect the fibers. Also, it's a fire. Fire is a major problem in normal composites. So this is really just only one slide on the climate change. We see the temperature effect from 90s. This is from NASA, so we had to believe this one. We had the hottest year last year, and however, this is not included. This is finishes at 2022. But see, when you draw like that, you can say, no one can say climate change is not happening and temperature rise is not happening. So that's the 2022. So it's real. That's why we need to do something to the environment. So net zero concrete to start with, why we are doing that. So construction industry uses about 1/3 of the emissions of the world, and half of those comes from two materials actually, steel and concrete. So we use 0.5 ton of cement per year for every person alive in the world. We don't even know how many people know that we are using half a ton of cement each person. So when you look at the numbers, so it's huge consumption of cement concrete. Probably that's why we all are there in concrete. Maybe one of the reasons. Because it is the material, the second most popular material after water. So how can we reduce or remove carbon emissions? We need to really do this one. So there are a few options we have. We can have using less cement. We can have, today I'm not going to talk too much about optimization of structural elements. We can optimize the section. That's why company like CSEC always doing optimization of the structural elements and to get the best out of the materials. So really we can reduce the sizes, we can do all sort of things there. So increasing the recycling rate. Again, the recycled concrete is a key that we demolish the concrete and then we can reuse the material. Once you demolish the concrete, we can really go and reuse the materials. So that's the second one. And the third one is the geopolymers. I'll just touch on the geopolymers. The geopolymer concrete came so many years back. And however, we took about so long, 20 years. Maybe I'll mention that when I talk about geopolymer very briefly today. Today I have a limited time, but in the discussion there could be other questions. But so the fourth one is reducing the clinker content in concrete by using supplementary cementitious materials. I'll explain that. So to get to net zero concrete, low carbon concrete, we already have got low carbon concrete. We have, but we have to get to the net zero concrete, we have a long way to go. So this is what we also, as engineers and those who are involved in the industry, need not be just engineers. We need to be part of this engineering in the whole net zero system. That is what we all are here today, and to listen to me. We start with the basics. This is I use so many years back to teach students. I still do a couple of lectures on concrete technology at the beginning. As a senior person, I still like to do that at the beginning. Then I don't teach all the whole course now. But so if you go back to the basics, we need to get to the net zero. Only way is we need to get back to the basics. So the concrete volume, the 70% pillar, these are rough numbers. This can change, but these are, if you put, just to give some idea, and it is very important that you have a feel for it, the numbers. So the concrete volume is 70% pillar and 30% paste. So we have so what we do is, so it's only 10% of the concrete consists of Portland cement, about 20% is water. And then to reduce the cost, we fill with aggregates and all that. So it's like a glue. Paste is like a glue. So this is going back to the fundamentals. So to really have proper designing of mixers to many other things, we need to really get back to the fundamentals. That's the time that we had to do that. Then comes the cement paste. We have the cement paste. Then we have the superplasticizers. I think there are superplasticizers, companies here representing the companies. So there are superplasticizers. We made a change to the world of concrete, where we could go down to the water, we could reduce the water cement ratio and have the superplasticizers to improve the workability. So that's a key area happened in the world, having the invention of the superplasticizers. The concrete invention happened a couple of centuries back, but the last century, one of the best inventions was the superplasticizers to improve the workabilities. And it's a growing area, and I can talk for hours on superplasticizers, but I will not do that today. But and then the silica fume, and then the other pozzolanic admixtures came to the world with the waste materials being converted. We didn't know what was silica fume, fly ash. We didn't even know. Again, I've been in the industry for so long. I know how the beginnings of the beginnings of the fly ashes. I had to we had to mention the whole world has thanked one Professor Malhotra, who brought fly ash to the world in terms of he did some evidence-based work from Canada, CanMet. As a young academic, I had a chance to go to Canada CanMet conferences and met Professor Malhotra. I was so happy to see him in India a couple of years back. That when he came to, he's very old, but he came to Mumbai. So was very happy to see him there, and I acknowledged in my talk. So coming back, this is a graph that I use, and getting back to the fundamentals, that's where we are. We have to really get to the net zeros. We can't just touch on what is happening in practice and all that. So on the y-axis, there are a number of, the young engineers here and young engineers and others in the construction industry here. So this is where we should start. The surface area on the y-axis and particle size on the x-axis, and see the evaluation of concrete. So we started with the large particle sizes on the right at the end, and then we had coming down, coming to the left, natural sands, Portland cements, fines, and then we had the fly ashes came later on. Again, the particle sizes were lower, but then we are increasing the specific area. The particles are becoming smaller now, and smaller. Then, so see the performance improves, and then we get to the conventional concrete is on the right, and the high strength, high performance concrete came to the world, and some of us were there, from the beginning of that journey. So coming to silica fumes, metakaolin means clay, which I'll have a few slides there later on. And then the nano-engineered concrete. So where we nanosilicas and all that. I think Dr. Tushar, your PhD was on nanosilica. I was happy to be a supporter of your PhD. One of the supporters, of course. The nanosilica, the precipitated silica, which is nanosilica, and of course nanosilica, but these are special ones. But because of the production processes have energy and all that, we are not, for the net zero concrete, it's hard to use that. One day it will come, so I will not touch on that part. That's for some special type of concrete. We still have to really, this is from a graph of some of my work in, I don't know, I wouldn't say the time, but then, I can't remember now, but the stress versus strain, if you draw that, again, the basics going back to low strength concrete has parabolic, because going to the top, there are microcracks forming, and it can really absorb the energy. So it goes down very slowly. But medium strength, getting to high strengths, is very brittle at the top. So very brittle at the top, and then it's just to really, you need to do something to improve the ductility. So high strength concrete, that's my work with the Burj Khalifa. That is to really improve the ductility of the columns by having more stirrups or more ligatures. That one it's another day, that talk. That I will not, unless there's questions on the discussion. They're all here. If you want, you can. I think this book I wrote in 2000s, early 2000s. So it's all in there. So we need to look at I'll talk about the materials side more. Today, the talk is more on the technology and the materials. But so it's the high performance materials for the future. And so we need to look at the performance side. We need to start from the performance. It's in the lightweight. And I know, Mr. Tilak, your module had to be lightweight, the high strength, get into the high strength. The fire resistance is a key. So we can do whatever with the materials. And actually, Sri Lanka's expert in fire resistance is here, Mr. Vajra, Aero Solutions. They're doing lots of work on trying to protect the protect the structures from fire. The high strength durability is a key where the durability has to be looked at. The affordability and it has to be affordable. We can't just go and do everything just because we want to get net zero concrete. We can't spend millions and millions. Then it's not going to go to the actual structure. So we need to be affordable, environmental friendly. That's what we are doing this now. So you need to look at the performance overall when you look at the material as well. Acoustics and all that are secondary, but very important. That there's sometimes sound barriers and all that are so important. So what we had to do is to really to use the zero carbon or low carbon materials. And we need to really get into the practices. Only way is to the evidence-based field applications. We need to look at the field and collect the evidence now. So we have to start working on putting something here. I'll give an example what happened here. But so this evidence base is quite important. So the performance-based standards and specifications are quite important. If we don't put in the standards and specifications, then it will not go to the practice. That's what we want to do. So all three come together. They combine together. So a zero carbon future, where we are. The last year I did a national seminar series in Australia, going down every city, talking about low carbon concrete. This is a slide from there. But the embodied carbon is on the y-axis. Here is on the x-axis. And again, to really reduce to the critical period, let's not worry too much about what's everything there. But look at we need to get to the net zero in 2050. So we are already 2025. And so I think we have only 25 years. And even 2030, we thought we should get somewhere. But I will not touch on the UN SDGs and all that today, but we are really behind. And even 1.5 degrees is not going to happen. We are going to at least have 2 degrees in 2050. So we are behind on everything. So that's why we need to get solutions very quickly. So it's a critical period for change. I think I need to put that arrow now a bit more further. I don't think we'll achieve that in 2035. This one, I think I was done in 2020. So we said we have 15 years of critical time, but not much has happened in the last 5 years, actually. When you think of yes and no, people are doing a lot of work, but in terms of progressing totally, so net zero, we should have had net zero concrete by now in a big way. We don't have that yet. So we have to really keep working. So this really, no need to read too much, just to show that the after water concrete is the most consumed substance in the world. Produces 3 billion tons of emissions. And concrete itself, huge number, 8% or more, from concrete itself. So 1 ton of cement emits 1 ton of CO2. And then concrete is 0.9. Now, we need to know these numbers. Finally, it will be a numbers game in the future. Because any project now we are assessing only through cost. But in the future, it's already happening in countries. Australia is happening. And Singapore is even going to be further like that. Europe has always been doing this. That is, you need to show the carbon numbers for a project. We can't just go and say the cost is this of a project. So we need to inform. That's what we are doing here also, informing carbon numbers. So just for a lot of people don't know why concrete is the problem. And like knowing this, some of you, but this is the problem. We have the limestone. I'll show you the next slide. Actual process. Limestone calcium carbonate is used for cement production. It's heated at about 1500. So to convert it to lime means the key ingredient of the concrete. And so carbon dioxide, CO2 emissions come from that. So it's really, so we need to do something and attack at that level. So we need to really to do something to that. So this is really a basic diagram of cement manufacturing. If you go to the cement manufacturing, the clay and clay and limestone are mixed, calcium carbonate, and we go through a raw mill, and then going through a rotary kiln. Then you get to what's called a clinker. Now, that is in the rotary kiln. It's really again heated to first to 900 and then to 1500. So that's where all the carbon dioxide goes out. So we need to attack at that level to really do something and deliver a gypsum is added, and then also the chemicals produced. So it's really like the combinations like this. So the calcination. Now, what is happening in the world? It's just starting to happen. Even companies are now in the process. I told you that calcium carbonate is but carbon dioxide is captured. The carbon dioxide is captured, and then the first process is capturing like that. The carbon dioxide. Australia is that is they are trying to capture that carbon dioxide. So that's one of the things. Then what we do is that carbon dioxide. So, coming back to that, the low carbon concrete, this really, I'm not going to talk about theory so much. I have very happy to answer questions and then communicate or the technology going deeper into this. This is what our ideas are specialized at here. And from low carbon concrete, where the next low carbon concrete is zero concrete, we have to really definitely clear. We are, first of all, there are a lot of experts in this, that is like the characterization, technique, that is also, we are saying this is something no other place in the world can do this, that is using a good technology and the structural to the best. So that's what the term I can say that very short problem. There are very good technology groups in the world. There are very good structural groups, but I don't think that's good. There are experts in the both sides. On the right-hand side, when you see the characterization is quite important. The X-ray-based testing, words, there are other ways of doing exporting. There is a microscope-based technique, FDA, but are there, again, we talk about And I don't know if we do that. Then we do that for from nano level. We have and then the nano scale, micro scale, each scale then gets by the visible. We take one more. It's the first one more. Wait, wait. We'll adjust it because I think very difficult. No, maybe I'm too close to you. No, it's okay. Better. I can ask the audience. Are you listening? Better? Yeah, so I think just try now. Oh, yeah. I just tried that content, but so starting from the molecular level, which is nanoscale, coming from that, and concrete is very hard to really model right through. So this is the one with cement phase going to cement mortar, concrete, which is at the mesoscale, which is really the climate and all that. So we continue, and I will not spend too much time on these things. I'll tell you why. Uh, this is really, we need to look at both technology to get to the net zero carbon. We need to get to the both sides. I'll leave that to another time to explain in a bit more detail. Yeah, sure, that's fine. So then again, that what we're doing is characterization. Like we do the material and we link to the structural to this what is called a new technique, nano indentation. I think Anuradha is here, one of my best PhD students, have completed. She's I'm sure listening today. So she's working on with from materials to the structural level with the nano indentation. So we have done some world type of work with that. In that work, she's looking at basically with the visual technique to look at the amount, the fraction. That is, the quantification is the key. So this is working towards the net zero concrete, and there's a lot of detail here, but we'll not explain too much. But there are papers written by her, be available, and with the so with different materials, and then getting with the different colors, we can identify the concrete's main component with the PSH. And today is not totally a concrete technology lecture, but I'm happy to explain the questions. But PSH, which is the key component of the concrete, is formed and from that portion, the fraction is 44. So quantification. So we use a technique, they use the EDS based technique for EDX based technique to really look at that. That's the findings of her PhD. So then she goes and doing the nano indentation, that's a nano indented, nano indenter. At the very small level, it can indent. On the right hand side, you can see that nano indentation. So nano indentation, the final graph is the force versus the displacement. So it's all about force versus displacement. When I talk structural analysis lectures, I say just that is what we want to achieve of a structure, force versus displacement. So we can do all sort of other things. So here we are converting the materials to the structures. So this is the most difficult task. We're looking at the material characterization and converting into the displacement on the like structural level. So this is going to be out this year, as is June 2025. That's again the first in the world book on multi-scale modeling of concrete. We will thank my team, Dr. Sana, who was here with us in the Candy Conference, from my former PhD student, and Dr. Sadiq from Moratua, I think that's Dr. Sonny means that, of Moratua, and then Dr. Son from Macquarie University. He has worked very closely with me right through his journey of nano indentation. So, and then Anurag also introduced to this now. So, so you can read that. Coming very briefly to geopolymer concretes. So the geopolymer concretes are where the again I will not touch too much. This is really for the especially for the younger group. What is the geopolymer concrete with the solids? You can have the what is called the precursors. You can have any material which has the aluminiums and silicons and all that with the clay, slag, all sort of material, rice husk ash, silica fumes, fly ashes, and again, any of these materials, and with and then we do what are called add some alkalis. So we can read about geopolymer concrete later on, but if you are not familiar, but so the alkali activation is the key. Use the alkalis to activate this material. So it's a sodium hydroxide or sodium silicate are the ones being used. And then you get the alkali solution. Again, the world level, what's going on now is to really have natural activators. We are going natural for everything. Right? So with the natural, the chemicals being replaced by natural materials. And it has to be done very slowly, the chemicals, organics, like the chemicals to be replaced. So we can't do it straight away. But this is happening, the natural materials, rice husk ash. We are looking at rice husk ash and another one called red mud. That is, red mud is coming from the bauxites, the aluminium process. So you have the alkalis, and it's amazing that this is one of the main inventions last 30 years, thanks to Dr. Devotetis from Europe. But his main person, I was very fortunate to work with Professor Gianni Van Deventer. He did a lot of very good things. He's a chemical engineer, materials. I brought the structural side working with him. On the geopolymer from early stages. So this geopolymer concrete is cementless concrete. And again, I will not cementless again, this is a world development. You look at 5 years, next 5 years. We just got a grant with a professor from Sydney Uni. I had to acknowledge Professor Gandu Karansi and myself. We got a government big grant to really work on cementless carbon negative concrete. So you are hearing for the first time the word carbon negative concrete. So you'll hear with next 5 years of our work. I can't disclose everything what we are going to do. But today I'm just looking at zero now. Before we get to negative, we have to get to zero first. And coming back to all that, the geopolymer concrete are one of the key. ones to really cementless. But however, we can't, my thinking is we can't have cement. I like to have some cement around, cement to be mixed. So even with geopolymer concrete, we go and say, let's have about 20% cement even. So I'll leave that to another time. So geopolymer concrete, cementless concrete is again a zero carbon type of concrete, but we need to do other things for that. It's a basic one, but only problem is that it's not accepted totally for structural concrete yet. So what we did in Australia is, I was also part of that group, but we came up with TS199, which is for alkali activated materials. So and geopolymer concrete, one of the main ones. And we recommended for structures. So we may come to the structural level, but very little structures around the world on that. Anyway, I'll leave that to another time. So we need to look at the properties first. The OPC, and this is the geopolymer concrete. This is a very good comparison of this is not the direct comparison. You can work on OPC concrete and get to that side as well. Same time, there are geopolymer concretes are not as good as what is mentioned here. So we have to just very carefully work on that before we totally replace the OPC. So some of the applications are being there. So I will leave that for now, and people are starting to apply. But even geopolymer concrete has been there for this was 1975 or whatever, till 80s. But then still we have not got geopolymer concrete. So, but we can't wait. Anyway, this is really briefly my talk on new things, where so I just summarize. We just summarized. Again, I had to thank Anuradha for giving me doing some slides for me from Melbourne. These slides. So carbon capture and utilization for concrete production, where the carbonation of recycled concrete aggregates. I will mention that, and also this really summarizes where the world is at the moment on zero carbon concrete. And the magnesium oxide based binders, I'll just briefly mention. And then also there are other things can be done, like carbon dioxide curing. So I'll start with the last one, where there's a company called Carbon Cure. You can look at use carbon dioxide to cure the concrete. So that captured carbon dioxide is put it under pressure to really have the cure the concrete and get higher strength. So these are some key changes there, and also carbon dioxide can be injected. So that captured carbon dioxide from the cement, cement production, can be used in all sort of ways to bring it back to the concrete. That's how you get the zero concrete, the carbon zero. So this really really summarizes my next few slides. So the recycled concrete aggregates, where we demolish the concrete. The recycled concrete aggregate concrete has two surfaces. One is the whole surface, where around the aggregate you have the cement paste, and then once you do it again, the concrete, you have another surface. It's got two surfaces. So the outside surface is bit weak. If we go into a bit more depth of the what is carbon dioxide will do to this outside surface, it really again when the carbon dioxide is injected, you see on the right hand side the diagram, the carbon dioxide is injected, and then it comes back to again with pressure, and sometimes you need some temperature to do that. And the outside surface, the calcium oxide becomes calcium carbonate, because calcium oxide in the cement paste outside layer becomes calcium carbonate. So that really process will absorb the carbon dioxide in the recycled concrete aggregates. And I hope I'll be able to do that here as well one day. We are starting to do that there in the labs, but there are no actually properly done in the world in a commercial scale. Maybe someone here listening today could start a business. I'm sure earn a bit of money in the future. And with so these are the how the recycled concrete aggregates. We can get the recycled concrete aggregates. Recycled concrete aggregates, we can at the moment replace only about 30% of the coarse aggregates according to the specification. And but however, what again, I'm leading a committee in our Australian standards subcommittee looking at recycled concrete aggregates some specification. By having carbonated like this, we can have even higher percentage. Maybe 50% of the coarse aggregates, we are running out of gravel, coarse aggregates, large aggregates, can be replaced by this recycled concrete aggregate component. I was very happy to see last year a company who has started to do recycled concrete aggregates in Sri Lanka, that's in Ahangam, with someone known to us. He told me he started because I mentioned in a talk 5 years back. The word I used is waste is gold. And he said he may get to gold one day from that waste. So, which is a true saying. I said this in other talk yesterday as well. But waste can be gold one day. Can earn a lot of money with the waste. Waste is not waste. So, anyway, coming back to recycled concrete aggregate, so that's one of the carbonation. Once you carbonate it, this is zero carbon. Once you get, because you captured carbon being used and to do something to modify the surfaces and can be this recycled concrete aggregates can be used. I know there are a number of people here. We invited only a very small group because we have a limited space, but thank you for to be here. To some of the admissions companies are here as well. But your superclass, I would call that, are quite important. That's very important to get the proper properly the work for these materials. Well, so having this is something you will hear a lot more. I'm talking about the next 5 years to 10 years as well. I had to say that out my group. I started doing some of this work, but there could be other assumptions as well, but doing these things. But with the so in this case, magnesium oxide, I'll tell you the reason. We always go to basic, and the reactive magnesium oxide cement, again, in this case, with the why magnesium oxide is very important. Magnesium oxide based binders, I'll show it in the next slide. This is very important. So, in this case, the CO2, magnesium carbonate based cements, which is going to come to the world, has the potential to become a major carbon sink. The CO2, so will be again two different reaction mechanisms, setting and hardening of such cements. Again, hydration of, is going to detail hydration of magnesium oxide and magnesium carbonate, also blending with silica and other mineral additions in the presence of water or salt solution at ambient temperature. So this is the main way of the hardening. And the second one is that the carbonation hardening of magnesium oxide based systems at increased carbon dioxide partial pressure and at increased temperature. So that will harden these magnesium oxide based systems as well. So then that captured carbon dioxide from the cement production can be used to really for these binders. And again, as I said, this will be more. So back to basics. This is the one. I don't know how many people listening knows the periodic table. I did chemistry first. We are civil engineers, but I do chemistry. And then I still remember the periodic table with the so if you look at the periodic table, So again, get to these levels, you need to go into the basics. I always tell my students, you need to really, don't forget your chemistry. Like the, the magnesium, and see the magnesium and calcium, which is the main component of cement, is in the same group, which is called group, the vertical in the periodic table. And again, it's in the same. If you want to go into detail, it's got the same number of valence electrons and similar chemical properties. Then, so we can really now. I think we don't spend enough time. You may be able to go down to this quantum at the bottom of calcium. So we don't need to. So getting back to the basics, calcium oxide, that is a problem. Calcium carbonate right now emitting the CO2 calcium oxide. So and then let's do something with these ones with having similar chemical properties. So that's how the magnesium is. And we could look at some other materials as well. So periodic table still so important when it gets to when we work on cements. So this really again a summary of that. Where I'll show you where the magnesium silicon are coming, and this can be dissolved. You don't need to heat it. You don't need when you heat to that 1,500 as I mentioned to cement production only, you get that CO2 content. But in this case, it gets to the binders and the magnesium oxide are created. That can be really, and the hardening process, as I mentioned, it's with the CO2s and all that, and then that will really harden. So because why concrete is the best materials being invented in the world, one of the best materials, is because the concrete is hardening. The cement hydration reaction. So we are replacing that cement hydration reaction with some alternative way. So we need to come up with some alternative ways as well. We have to continue what we're doing, same time to get to that ways or the negative carbon cement or zero cement, zero carbon cement. So the other things I'll skip there. So that means on just to show that can be done. So in this case, the other method is the carbon sequestration of fly ash. That is carbon. Again, I will not spend too much time. Again, I say come on rather work. She has put the source there. We can look at that. The reference starting to come to the world. This is a very new. That is carbon dioxide. We want to do something that captured carbon dioxide. So we can push it through fly ash. We can push it through slag. That really gets better material. And we already talked about carbon dioxide pushed through the recycled concrete agriculture. So that is how you get to the net zero. You can read about the fly ash. I can spend time on that, rather than that. It's very generally is where the world is. So not to worry too much of detail. You will hear a bit more. It's 5 years on this work. So it is really the sequestration is like that. You get to the accelerated carbonation treatment, as I said, with the carbonation, carbon dioxide through the materials, and then going around the loop, and the resource efficiency, and then final concrete elements and structures. So it's a cost and energy efficiency as well. So again, the carbonation curing can be done, carbon curing, to get to that the zero carbon level. These will become, certain things become routine in 5-10 years, just maybe 10 years, not 5 years. But this is something very special. It's like close to me. There's a material which is called olivine, which is coming from some volcanic rocks, and we have in Australia, but there are other countries as well. So olivine is magnesium ferrous SI, silicon oxide. It's going to be chemical detail of it. So that is really absorbs carbon dioxide. So magnesium carbonate, again, just believe me, but magnesium carbonate, and then you mix with some silicas. This work we are doing now, but then you get to the next level. So this is really a way of attracting that natural rocks available. I in fact talked to someone in our geology. She's done a PhD. She has a link to Sri Lanka. It's not from Sri Lanka, from Australia, but I think Australia is Sri Lanka. Anyway, so I talked to her about the olivine from that side of geology. But the magnesium carbonate with the silicas and then you get to the again. And so this is one of the ways. You will hear a bit more from our some of that work on that possible. So the calcium clay cement. So this is really a something I had to just acknowledge Karen Scrivener from Zurich. In fact, she's the first one to come up with calcium clay cement. So what we're doing there is that the OPC, the gypsum, the OPC clinker is essentially where to reduce the clinker content. So to really get to that carbon, reduce the carbon. So with the fly ashes and other materials also, you can reduce it a bit more. The blended cement. At that time, I remember I had a chance to launch the wholesale at that time. I think Dr. Pichari invited me to launch the blended cement and it was enough for both of them. Invited me to be there. But the PPC, I think probably both of you came up with the PPC. Right? Yes. So the fly ashes, I'm sure there are questions for fly ashes. Then the calcium clay, the limestone. In this case, calcium clay is just clay. I was saying other day in a conference here in somewhere, I can't remember where in Colombia, but or a talk about we have clay. We have clay around, and so calcium clay is limestone. You mix calcium clay. That's what these Rangada there. I think she must be in the district. So she's doing this work now, and with the calcium clay replacing some of that calcium clay replacing like fly ash. It's like fly ash, totally limestone, and it's okay. Thoroughly your work on your undergrad work on bricks, trying to put. So bricks are a good example of the calcine clay where it's a clay where bricks are already calcined. So you have the bricks being like when you touch the bricks, you already get some phosphoranic activity at your reflecting fan at that time. But if you touch it a bit further, they get to the phosphoranic. You can try it. That works. So that is LC3, which is really getting popular. The calcine clay cement. I was in IIT Delhi last April and IIT Madras. They are also part of that group working on that. Thank you, Mr. Omar. Already acknowledged you. I know you had a beauty with your communists, but thank you for joining for the So into the calcine clay cement with replacing. I think this one we will hear a lot more. Sandra's work we will see next year. We are working with a quarry in Melbourne, trying to have the calcine clay and really use that. It's not really in the practice yet, so we're trying to get to the real practice. This work. So LC3 you will hear a lot. I will not go into theory too much. That's the work. But we work on looking at the temperature strength. We're getting the clay. This is just a waste clay, and some of the temperature strengths with these processes. But you need to calcine them with the with a very high temperatures and so here, why don't we see is the main question. With Amra that put these questions, but why don't we see calcium clay cements at industry scale, lack of confidence to use new mixers. Most of the clays are not highly kyolinitic. I will not spend time today. Another topic we can talk for some time. But the kaolin content is quite so important. And the early edge strength gain is slow. So what we will be trying out in that project is maybe use some graphenes and whatever to graphene oxides to give it more strength. So we can have some new materials, new things to do, play with some materials, trying to get to those numbers. So there are other ones being identified. Again, I thank you, John Robert, to identify from his work with the materials, some of the materials that we can use to replace and to really have replaced coming up with some phosphoranic materials to really replace not only it could be sand, it could be replacing replacing cement even. And this is what you're saying. We're talking about pots. Sri Lanka has a lot of pots. So so many pots can be used for concrete. Because we have very pure pots. I was told 99.8% purity. Our pots in Sri Lanka. So these are some of the things. So we can look at all that. This one is, again, we are doing some work. Again, today I'm not touching on graphene with LOC. Again, Shara himself encouraged me to really understand there. It's really using graphene concrete to use because they're producing graphene now in Homagama. So the graphene oxide, so we are using graphene oxide concrete. We think it will improve the carbon absorption of graphene oxide. Actually, who is there, one of my students, he's looking at this graphene oxide, the carbon absorption. I'll run speaker. That's after we're running out of time. But so recycled materials in construction, we already talked about some of the recovered materials, the concretes, the timber, we had the gypsums, roofing, we talked about bricks already. So replacing some of these recovered construction waste in the like now to really in our again reuse them as construction material. So we can use some of them for our fluorocarbon. Replacing glass, paper, textiles, tires, solar panels. I'll be very quick with running this. But the graphene oxide, I will do another talk about this. That is in detail. Another webinar talk. So plastics, rubber, touch glass, bottom ash, Mr. Chomal has used for the staircase here. Total bottom ash. So that is the not fly ash, but you get bottom ash. Fly ash is used a lot, but the bottom ash is really something that we need to try it out a bit more. The recycled concrete aggregate, I think Mr. Vajiros, we talked about bottom ash. But anyway, recycled concrete aggregate. So these are some real applications. This is where I'm proud of the group. Looking at glass, replacing the sand in this project. We got work with Holcim Australia to really have glass in concrete. So it's part of the net zero concrete. We can use other materials to. So concrete is not just cement. We talked about cement before, but we had replaced some of the sand and also we can't use natural sand all the time. We are running out of natural sand. So we are replacing. Otherwise, they just go to the landfill. This has got carbon numbers. To get to that net zero concrete, we can use all these techniques. This is the first time being used in large project, the glass concrete. The problem here was, that's why it's important. We don't see this in the lab. The glass hitting the pumps. So we had to adjust the mixers we had to adjust to some superclass sizes, workability, work with the superclass size of companies to come up with the workability. And that's what important. So all these materials are important, not just one material. Right, so that's one. It's another one which really with where we put solar glass because we are if at solar panels, we had to replace the solar panels. So where is it going? There's nowhere. I don't know where they are thrown here somewhere. But they also we were thrown to the landfill, but now we're not allowing them to be thrown to the landfill. So I had to thank Mr. Viraj. He owns that company, set up a company, invested about $6-7 million already on his plant, crushing the solar panels, separating the polymers, the back panel, and again the glass. That is the project that I believe in as well. The sort of finished one out, but it's a very good outcome. Yeah, we can look at solar crete is the solar glass. Solar crete is the name I gave. It's really opposite picked up the name. We have that. So we are again the plastic done by Dr. Arnett is leading this one project where I will not show the full video. I'll show you why net zero concrete. To make concrete structures, you have this white form. Normally, these white forms are done from the polystyrene or the rigid forms. So rigid forms are going out of the world because they can't be when we go to landfill, really dirty and all that. So slowly being banned in at least one state. We had to use in construction, of course. We can't do much, but here the robo is sorting out the plastics. The plastics are used for this. On the right hand side, the white forms on the slabs. So that's how the carbon compound gets reduced. So robo is very slow in this case. The video is slow. I think the robo is done. This is all done by it happened to be a Sri Lankan team. That is, one is a mechanical engineer, one is electrical, one is civil engineer, other person is computer science. So it's a multidisciplinary team. It's really good. That's the robo picking up nicely the different type of plastics. So these sort of techniques, you can use AI integration. AI integration is the key to get the properly done. It picks up properly. This is now adaptive. I had to show you this place. But so this is one of the first in the world. That is this is the slab. This is the one better than me. Of this one, where when we're doing the slab, we put everything here. This slab. It is really you are here in this lab. Underneath is all sort of waste materials. Don't go away because it's waste material. But it is really a good application where all that. And we put graphene oxide to really bump up the strength a little bit. So it is very, there are no cracks. No, guys are not cracks. How many years is this one? 3 years? Must be. It's past that age where the first 2 years normally we will see problem. This part that this is the evidence base we have to create. Use this in real area, and this all being there. These are the materials we use for this lab here. This lab here, which is the plastic, rubber, crushed glass, bottom mash, recycled concrete aggregate. And we found some textiles as well, and we found some hair. I don't know how we found it, but we put everything here. When we're doing it. So I can go on and on because we are running out of time. So I'm sure there's some time for discussion. So I have to really thank our research group. That's why I can do all this work. And it happened to be we got other non-Sri Lankans as well in the group, but it's more of a Sri Lankan get-togethers. But the labs and then this is the site. I think some of the screens is probably I'm going to put this slide, but from the there. So again, the last one is we all get together and we have a thinking session as well, not just research. So just I have to thank my district group. I think coming into zero carbons and concrete technology and linking structures, I definitely consider to be the rest of the world. So I think thank you, Mr. Smith. Thank you very much. I'm going to take that.
Thank you, Professor, for that very insightful and comprehensive webinar on zero carbon concrete. I think everyone gathered here today and also from the YouTube live session gained valuable knowledges through your experience and expertise. So we can move ahead with the discussion. So we have one question, Professor, from Sanuya. If magnesium is used instead of calcium, then how about the hydration temperature of concrete?
Extremely good question. So I think that's something, yeah, I expect it to be because it's a very good question because the hydration, maybe we can look at it in a positive way. That's how I think. I haven't done this work yet. Maybe something we can check. The reason is because that the formation of cement hydration reaction, different type of ingredients in cement will create that lots of heat, and that's why we had to be very careful about thick elements and all that. Also, even for other elements, when the temperature increases, concrete has got some micro cracks, and there are other problems like the delayed ethylene formation happens at high temperatures, all that. So again, my thinking is that we're very positive because we are not using that sort of similar hydration reaction to harden the concrete. We were talking about the carbon dioxide sort of processes to really carbonate and so on to really get the strength. So maybe very good question. Maybe that's a bit of advantage to have the magnesium oxide based cement in the future. So that especially for mass concrete elements where heat of hydration could be a problem. So the short answer is my thinking is to be other way around. So heat would be less that because of the chemical processes are different.
We have another question from Mr. Amit. He says that in Europe, low clinker cement is effectively used due to strong regulations promoting the use of recycled aggregates and green concrete. He's asking whether we should implement similar regulations here.
Here can be there's so many kind of people are joining from different countries, so we assume it's not good. So with the regulations, again, I was saying this yesterday also in another talk, but Sri Lanka is very progressive, and that's why I think Mr. Shomar may answer this one, that we could put all sort of waste materials into this lab, and of course, because we're signing for that. But still, maybe I like it. Like comment from you as well for this one. But the reason is that again with the regulation to get the approval, I can't do this in Australia. So because of the regulations, our recycled concrete aggregates, I have started again another group under our concrete structures committee. I'm leading that one to have some guidelines for recycled concrete aggregates. So this is where we are putting the standards. Once we put the standards, we can use it. But at the moment, we can, as I mentioned, replace only about 30% of the post aggregates. So we know we can replace with first, but it's really it's only 30%. So what do you think here the regulations will allow us to use, because here it's a bit better, because I'll just mention that I think very good answer to the, because just for the online audience, what Mr. Shomal is saying is that because structural engineers take the responsibility and sign off if something goes wrong, the structural engineer. So it's no risk for no one will put barriers into that. And that's why I think we have to approve other materials as well for the concrete. So the engineer has to sign off. So it's slightly different in other countries. Good question. But if it's in the standards, we can use it. Going away from standards is very difficult. Sometimes we have to sign off as board committee members for certain things, producing fiber reinforced concrete, all that. So maybe let's take one more question because I don't know.
Question is from Vinu Gunathilaka. It says that recycling of solar panels is in the works, are there any commercial incentives for Sri Lanka in processing some of these waste, as countries like Australia has a lot of red tape?
Yeah, Australia has red tape. Yeah, that's correct. Yeah, so yeah, so Australia has that is a very good point where the Australia is very difficult to get through, but in this case, the solar glass, we are going through it's a very good point being mentioned. We are going through with some other projects, infrastructure projects, trying to put this solar free. So there are issues like that, getting the approval through the system. But we know it works, there's no problem. And we can show, so we have to go and show the authorities that there's no issue of that. ASR is a major issue, alkali reaction, as correctly pointed out. But we are crushing the glass. Today, I will not have time to talk. Crushing the glass into smaller particles. So we think we have done in the labs to show that ASR problem goes away. That's why people are scared over this alkali silica reaction problem. I can talk about that on another day. So it's a very good point. I think again, Mr. Omar knows about these fundamental systems here. Here could be a bit easier to be against structural engineer taking the responsibility, so can sign off, and so we may be able to get some solar glass into a project, maybe your next building. That's a very good point, Mr. Mark, because yeah, that's what I mentioned before you came, but we are working on some carbon negatives. But it's a very good point. Not just cement. Like, no, we just work on cement, everything. But I mentioned first some of your work, like the optimizing the structures. That's also part of it. And rather than, like so the whole carbon zero or negative carbon is exactly what you mentioned. Overall carbon numbers we have to calculate. That includes the sizes of the members. So you have to attack on the sizes, optimization of sizes. Then you need to do the cement part. Then you need to do the replacement of the sand. We talked about post aggregates. This overall process, exactly what you said. So we need to really, our carbon number has to come up. So it will be the normal benchmarking, normal concrete versus this one. It's really, we do all sort of things to really improve that with the sustainability side. You're right. Can be carbon negative by that calculation? Less than the normal concrete. So yeah, so Mr. Yep. Very, very good point. And the it's again uh, that recycled concrete aggregates now, as I mentioned, 30% is the one being standard, like allowed. If we allow a bit more, definitely recycled concrete aggregates replacing the processing, that's the processing cost. So and then you get to the to that the replacing the post aggregate. But you had a very good point. But the carbon number is now is essential to calculate, not just the cost. So with the cost side by side, you need to give the carbon number, and it's compulsory for the at least Australian context from July 1 last year. Every construction project they had to report how they are going to reduce the carbon. So that reporting has to be done. It becomes compulsory. So there are policies out there which really encourage this. But you're right. In Sri Lanka context, the cost could be the barrier. So what do you understand? But Cecil, I think one was doing it now. He's all right with the cost thing. He's doing well. He's doing well. I mentioned Hangama. We went there last week. Last year, yeah, June. Maybe last December. Like he's doing all right with the he's converting all the cutting all the concrete. He's getting like one plant in his place, and then he's using it for some precast elements. He's doing work by CCS. Yeah, you will know. So yeah, no, it's really you're right. It's really it's going to come here as well with the carbon numbers. One way you're right, we can't compare because our case there are different economic conditions. That, however, like the thing that you started the modular factory, right? I'm sure there's some investment. There's a significant investment on that. It's like that. So you barely started that modular factory. So now it's picking up. It will pick up. Slowly it will pick up, and there are obvious advantages. The time, right? The construction time to and less waste is a good example of carbon. I talked about it yesterday about that. But so you're right. It's just those numbers. Even Mr. Kumar may have an opinion on how. We'll be running out of the post aggregates, right? We can't just have those quarries all the time. We are running out of them. And Australia, we were told yesterday, Sri Lanka may have a still big problem. You mentioned river sand yet, but Australia, we already have a problem with river sand. So we don't have enough river sand. So, and the prices are going up. So obviously, although there's a processing cost, the glass and all that will be, the cost will be, it's already matching. Solar crete here, the solar glass with the processing, about 1.5 times the sand price. But that the infrastructure project, they're happy to accept it because there's a huge carbon number saving for them. And it's good for their project to say they're using these. I don't think projects they can just say this in the world, they're just using routine things. You need to really come up with some innovations as well.
Thank you, Professor, again for that discussion. I think it was a good opportunity to all the participants joining online, as well as with participants who have joined us here today as well physically, this session. And I would again like to thank Professor Priyan Mendes for his time and commitment to make a knowledgeable society conducting these kind of webinars, and also all the online participants and everyone who has joined for joining the webinar, and also all the external participants who have accepted our invitation and joined us today here physically. I think this made the whole session more engaging, and we could share knowledge with each other. So thank you again for joining our webinar today. We hope that it was very beneficial to all of you. Thank you, speaker, once again for joining. And if you are interested in our future webinars and upcoming courses or publications, please keep an eye on our social media platforms. The WhatsApp group and channel. The WhatsApp group and channel, you all can see here. The SDI, you all can, we have our social media platforms on LinkedIn, WhatsApp, and Facebook. So you all can follow them for more updates on our upcoming courses. And also we have another course starting on the 16th of January, which is the Primavera P6 course conducted by a professional in the industry, Engineer Atula Samarasinha, which will happen for 6 consecutive Thursdays from 7 to 9 p.m. So you all can join. We have posted all the registration links on all our social media platforms. So all of you are invited to join the SDI family. So thank you again, everyone. Have a nice day.
One last thing, thank you, everyone. Again, thank you to Engineer Andrea and Engineer Chatumi, the Structural Design Institute, for inviting me to give this talk. As I said, the first time I'm presenting this topic, I'm a little bit slightly different, but I presented Korea in May. But early May, but other than that, the first time I'm presenting. So this sort of discussion is starting now. And thank you to Structural Design Institute. Thank you to Mr. Shoman, always encouraging these sort of knowledge-based activities. And it's a free seminar. They help the whole world to having free seminars. So it's the webinars. So it's really that service adding to the knowledge, not only to the Sri Lankans or other countries that we're joining today. So we have, I think we had a reasonable audience. Oh, 600. Only give a copy, going to copy over. That's it. So, but anyway, no, I think I'm going to go. That means the message is going. Well, publicizing that. It's good for Sri Lanka as well. Well, 600 people from different places, Sri Lanka and other places listening to this stuff. And it's a big idea, very slow in other countries. Here it's very active, but Australia is very slow. I can't do anything in Australia this week. You know, so still, I'm sure many people have joined. I don't know if she's listening. I'd rather have helped me with some slides as well here. It's very late 11 p.m. in Melbourne. But also thank you. I think we today we thought it was a limited group, so we couldn't. We had to ask one person from each company, but not more than that to be here. And thank you very much for all coming as well. And also, and thank you, myself, and now as well. So, with of course, Mr. Dilap, leading a very important initiative, and just been Mr. Vajra has done so much innovative things. And the next innovation is on nano plate in the fireproofing in Sri Lanka. So it's done some innovations, everything on retrofitting of structures in an engineer Vajra, and we see as well. So we in fact asked only few of our a few people today to be here. But I'm sure I'm online so many are joining online today, so I'm benefited from being with us today. And again, thank you very much.
Thank you everyone again for joining. Have a nice day. We will see you at our next webinar and conversation. Thank you.
Take a photo of the group here. Take everyone here. Please join us. Actually, there's a big group joining from rooftop as well, but I know it's they can't be here, right? Was it